Okay, so I want to make an addendum to the video I made earlier today on RC circuits. So I get to this point here in step 9, and I was explaining it, and I wanted to come back to it just to clean it up a little bit. So I'm not going to go over 10 and 11 here and just point things out. I'm just going to finish things on this side. So we get to this point. I said in the previous video, we're going to integrate this function here using this integral from the integral table, 1 over b log a plus bx. Well, this is going to be a natural log of q minus ce. So instead of 1 over b, it's going to be 1 over negative ce. It's in the same form. So I'm going to take this guy out here. So 1 over c, not e, but c over epsilon, which is a voltage. And then this is going to become natural log of q minus c epsilon. And it's going to be equal to this stuff over here on the right hand side. After I take the integral there, it's going to be negative t over rc. Okay, so at this point, I'm just going to multiply both sides by ce, leave the minus sign over there for the moment. So I have negative natural log q minus c epsilon equals negative c epsilon t over rc. So now I'm going to divide both sides by negative natural log, get rid of the minus sign. Over negative natural log. And so I have negative 1 over negative 1 over natural log. This whole business here. Let's see if I can squeeze it in. Well, I'm just going to push that down, and this is going to be in the parentheses. Okay. So this then becomes q minus c epsilon equals negative exponent, because the reciprocal of natural log is the exponential function, negative e to the minus c epsilon t over rc. So now we can all see how this is going to play itself out. So I just want to clear that part up. I don't know what part in the video, but once you guys get to this point, this is going to be the addendum. So I'm going to make a disclaimer that step 9 through 11, here's the addendum for that. And I just feel like I didn't clear that up, and I just wanted to make sure that this is all clear. So then this q, as a function of time, really, it's going to be equal to c epsilon for minus e to the e to the negative c epsilon t over rc. And I can just factor out a c epsilon. That becomes 1 minus e to the negative t over rc, and which we get at this point. So I just want to clear that 1 minus sign up, because on the previous video I did multiply by CE, but I didn't quite clear up why the negative sign goes away. So I just factor out the negative sign, and then I divide both sides by negative natural log, and so I come up with this final function here. This is a charge as a function of time, that expression. Okay, so that's that one part for charging a capacitor, and finding the charge as a function of time. So next thing I want to clear up is discharging a capacitor. And so this part here, I make it all the way through. So I just have my notes all out of whack there. So, well, not out of whack. I didn't include my limits were off. So taking us through all of this process and getting the expression for dq dt, which is enabling me to get the charge as a function of time in a discharging capacitor. So I get to this point, negative R dq dt, which is I equals Q over C, and I get to this point. So the capacitor it starts off at Q, maximum charge, then it goes down to small q. So because when I discharge a capacitor, I'm going to go from the largest charge to the smallest charge. So that means that whatever the charge was at the beginning, when you discharge it, it's going to go from large Q to small q. The charge is going to decrease. So let me erase this. I'm going to go, my limits are going to be large Q to small q. And then I'm going to erase this bit. I'll eventually come back to it. I want to clean this up. Okay. And there we are. So this is going to be natural log of the function q, limits large q to small q. So when we do that, then that's going to be equal to negative t over RC. So when we do this, it's going to be natural log of q minus natural log of large q, negative t over RC. And so using the natural log rules, this is going to be natural log of q over large q, which we saw, the expression that we saw before, and that's going to be equal to negative t over RC. Okay, let me erase this because it's also part of the end. So at this point, divide both sides by natural log. This becomes q over big Q, and that's e to the minus t over RC. And charge as a function of time is going to be equal to q times e minus t over RC. And that's charge as a function of time for a discharging capacitor. So as a capacitor discharges, this is how Q is going to vary through time. It's going to be a decay, okay? Exponential decay there. And so the current, so we're going to differentiating the function Q of t, we're going to get I of t equals negative Q over RC e to the minus T over RC. So I just wanted to clear that part up. Again, as I explained in the previous video, when we're differentiating an exponential function, in this case with respect to time, we're just going to take the part that doesn't involve time. So this is 1 over RC comes out of the exponential. So we're going to multiply negative 1 over RC times Q. So this is going to be negative 1 over RC times Q, or negative Q over RC e to the minus T over RC. And so that's a rule for differentiating exponential functions of this type. And so as a result, we're going to get, this is our expression for current, and this is our expression for charge for a capacitor that's discharging. So the charge is going to vary, it's going to decay by this function, and the current is going to decay by this function here. And a little note on this graph. Well, we can just show this for general purposes, but technically this should graph should start from negative Q over RC down here. Let me just go ahead and erase this. Okay. So everything else in the video you can follow. I just wanted to clean up the graph. So we have basically something like this. So negative Q over RC. The current is actually moving the opposite direction. If it was going from positive, in the first case, when we're charging a capacitor, we're going to have potential drop across the resistor. Then when we discharge it, we're going to have a potential gain, or the current's going to flow in reverse, but eventually it's going to decay to 0, and that looks something like that. It's going to trend towards 0. Draw that a little bit better. So that's something that it's going to trend towards 0. As t goes to infinity, e to the negative infinity, 1 over e to the infinity is just 0. So negative Q over RC times 0 is just 0 as t goes to infinity. And then the decay rate for the charge and the current is going to be the same. So when the time is equal to the time constant tau, it's RC, e to the minus 1. So that's going to be 1 over e, which is basically about 37% of the original current and the original charge, since they decay at the same rate. So this is going to be basically negative 0.368. And when t is equal to tau, so not to scale, but here's our tau, and we have a decay at the same rate, but in the opposite direction for current, and then likewise for the charge here. So that is basically what we have. I just wanted to clean up a bit on the derivation of those functions before for the charging capacitor case, and to clean up this graph for the discharging capacitor case, and also the function for discharging capacitor. I just was a little bit glib on the natural log part, and I just want to clean that up. And here's the graphs for the discharging capacitor. The charge is going to decay to 0, and the current is going to decay to 0 at the same rate, but this is in the opposite direction. The current is going to flow from negative to positive. And what that looks like again, we have the discharging case. The charging case, it was going that direction. With discharging, we're going opposite. And so that's what the current will look like, the direction of the current when the capacitor is discharging. So eventually it's going to decay to zero because some of it's going to bleed out towards the battery. It's going to keep coming back and decay exponentially until it's basically zero. Not quite zero, but all intents and purposes, it will be zero. Okay, so that's it on that. I will talk to you guys next time. All right. Okay, so yeah, last bit. Just wanted to clean up this asymptote. And for this is a charging capacitor case. So I'll just do a bold line. So again, when your capacitor is charging up as t is equal to 0, this whole function is going to die off at 0 because it's going to be 1 minus 1, so e to minus 0. So this e to the minus 0 here. So this is basically 1 over e to the 0, which is 1. 1 minus 1, 0. That's what we have here. Time constant is going to be 63%. And then eventually, as t gets very, very large, going to infinity, it's going to trend towards a maximum charge of capacitance times voltage. And won't quite get there, of course, because it's the limit. It's going to trend towards that maximum charge. So as I said before in the previous video, the charge is going to reach a maximum when the capacitor is basically the same voltage as the battery. And that goes all the way back to first principles of capacitance. So we see that trend happening here with this charging capacitor case. So it all fits, it all works out. So that's it.